Okay, so if you look at the graph of f of x equals 1 over x, kind of looks like this. You have your x, you have your y. It goes this here, and kind of like that there. Okay, so as it gets closer and closer to 0 from the right, it just keeps growing and growing and growing and getting bigger and bigger and bigger. But when it approaches 0 from the left, it just keeps getting smaller and smaller and smaller and smaller. So no matter what you do to that, it's not going to do anything. It's just always going to look like that. But with B, it's a little bit different because you can kind of manipulate it. Okay, so for B, g of x equals x squared minus 1 over x minus 1. Okay. Now, if you look at the numerator, that's the difference of squares. So we can make that g of x equals x minus 1 over x plus 1 over x minus 1. Which means these two will cancel out. So you end up with g of x equals x plus 1. The only thing is x still can't equal 1. Just because you removed it doesn't mean it completely disappears. It just means you turn that discontinuous function into a continuous function, but you didn't completely eliminate that discontinuity. You just kind of removed it for a second. So if you were to graph this, all you'd have to do is graph g of x equals x plus 1 and make it discontinuous at x equals 1, and you've basically graphed this one. So you have x, you have y. So g of x equals 1. You have a 1 here, a 1 here, and a negative 1 there. Oh, move that up a little bit. So this, move that over a little bit more. Well, that should have been straighter, but this is your g of x equals x squared minus 1 over x minus 1. Okay, all it is this graph, but it just has that opening at x equals 1. Yes?
That's because it can be in the denominator, right? That's why it
Yeah,
can't equal 1.
exactly. Yeah.
But what about, oh, it would just be 0 at that point if it was negative 1, right? G
Oh.
of x equals negative 1 plus 1, it would just be 0 at that point, and 1 back then.
Negative 1 plus 1.
If I'm looking at the bottom function, like when you had it, so that g of x equals x plus 1?
Yes,
It can
yes.
still be negative 1 at that point, right?
Oh, yeah, it could be negative 1. Yep, it would just be 0. Yep, so whatever would make it discontinuous or undefined in the first part of it, it would still make it undefined. It just makes it to where it'll be easier to graph.
Gotcha.
Yeah. All right. Any other questions on this one? All right. So if you're rusty on your factoring, you may want to go back and brush up on it because a lot of these have it to where you have to factor it out. Yep. Oh, anyone's still writing? Looks like everyone's done. All right. And we still have to do C.
So for a question like that, do we have, like, would it ask us if it can be removed or not? Something like a question like that, it'll ask us if it was a removable discontinuity that can be made.
Yep, it'll ask if it's if it's removable or
So
if
that's
it's
like the question pretty much, if it's removable.
yeah, or non-removable, and if it's removable, it may ask what is it.
Okay.
So that's about it. So all you have to do is just factor, cancel out, then say yeah, it's removable. But if you can't factor it and cancel it out, then it's not removable. So it all depends on whether or not it can factor and cancel. Okay, so for C, Let me write continued down here.
So that would be removable?
Yep, this one's removable. Oh, that's right, I didn't put that. Thanks for letting me know. Non-removable for the A and removable for B. Okay, so we're going to continue on the next page. Okay. So for C, now h of x equals x plus 1 when x is less than or equal to 0, and x squared plus 1 when x is greater than 0. Okay, so this is just a piecewise function. All it means that when it's on the left side of 0, this is the function you're going to use. So let's say first we'll start off with the function of x plus 1. So x plus 1 looks like that. Well, it should be a straight line, but so this is our h of x equals x plus 1. And our x and our y, this is our graph of x squared plus 1. Okay. So by this being a piecewise function, it's saying that, okay, all the way up to 0, we're going to use this one. But once we get past 0, we're going to use that one. Okay. So really, you just bring both of those together. You have your x, you have your y. Okay, so from, you might as well say negative infinity to 0, we're going to use x plus 1. So that means we get this half of it all the way up to 1. I mean, all the way up to 0. Okay, so then you stop. But once we get on the other side of 0, we use x squared plus 1, which means we use this half. Probably should do. So all we did was take each individual graph and kind of morph them together. Okay. So now we just made that continuous. So here you had a discontinuous graph, because if you just graphed both of them together, you would have had two graphs just kind of overlapping and just a mess. But here, you have a continuous graph. Because all it did was go here, meet up, and keep on going. Okay. Does that make sense? All right.
So this one's removable?
Yep, this is removable.
Question,
Mm-hmm.
wouldn't that be an open circle for the second one though, because it's not equal?
It would be if it would have picked up somewhere else, but because it's
It's picking up at the same
yep, it's
location?
picking up at the same spot. Exactly.
Okay.
So it's less than or equal to here, but just greater than here, so it picks up right at the same spot.
So if it does pick up at a different spot, then it would be an open circle?
Yep, then it would be an open circle. So if it would have picked up from, let's say,
Let's say plus 2.
yeah, so if you would have had x squared plus 2, it would have been x plus 1 here.
Yep.
And x squared plus 2 would have been the same graph, but up higher.
Yep.
So it would have been here, closed circle, then open circle, then it would have been that way. All right. Yes.
Now, what if it was less than, like, the first piecewise of it would be x is less than 0, and then the second one is x greater than 0, then it would just give, like, it would just be a hole at 0 at that point, right?
Oh yeah, if neither one of them had the equal to, then it would
Right.
just been an open circle.
Right.
Yeah.
It would still been a hole. Okay.
Yeah, exactly. Then it would have been discontinuous.
Mhm.
I mean, not discontinuous, non-removable. Because there was no way to make it continuous at that point. Oh, move that up, sorry about that. Okay, any other questions on this one? So this one's continuous on the entire number line. And it's removable. All right. Mhm.
Yeah, so what he said before, if it was x plus 1 and x plus 2, but it still had that 0, it would have a hole, but it would still be considered removable at that point, but continuous, or it would be
Oh, no, it would have
discontinuous?
been, yep, it would have been, well, this would have been non-removable. Because if you just graphed it where it was here, it would have intersected here, but
Right.
it would have been continuous across the whole thing.
Right, so it would just be non-removable.
Yep, it would have been non-removable. But because we kind of pieced them together, and we could have had it where it's starting off here, then it just picks up right there. Now it's just one continuous graph.
Okay.
Does that make a little sense?
I think so, yeah.
Oh, okay. All right. Any other questions on this one? Yes.
Why does it need to be classified as removable if it's continuous?
Oh, because the original graph is still continuous. I mean, discontinuous. But all we did was kind of create a continuous graph from a discontinuous.
So pretty much the original graph was pretty much that line plus the other thing over it,
Mhm.
which is like kind of like a weird looking, line and then a
Mhm.
U.
Yeah.
So when we remove half of the first one and half of the second one, we end up getting that bottom one, which
Yeah.
makes it continuous. That's why it's
Yeah,
removable.
exactly. So all we did was turn two graphs that they're not continuous everywhere. So you have one going this way, you have one going this way. They meet up here and meet up here, and they're just going all over the place. But here we created one smooth graph.
Will you ever question with us saying, make this equation removable, or, sorry, continuous?
Mm,
Make this discontinuous continuous? You understand
with
what I mean?
I see what you're saying. With this one,
Which is a question of continuity,
it would probably be more of a, is it,
whether it is.
yeah, whether it is or isn't removable.
It won't
Removable.
have us make it
Yeah.
removable or make it.
Exactly.
continuous. Okay.
Yeah, that'll be about it. All right. Any other questions? Excuse me. Thank you. All right. Okay. So we have a few properties of, I guess you can call them properties of continuity. Okay. Let's say if we let B represent any real number. Okay, it can be 8, 5, -4, 3.2, any real number at all. We just call it B. Okay. If f of x and g of x are two functions that are both continuous at c, remember sum is just, c is just some value, then the following are also continuous. Okay. So for one, the scalar multiple. That means if you, sorry about that. If you multiply a constant by a number, I mean not a constant, a function by a number, then that will still be continuous. If it was continuous before, if you multiply it by 5, it'll still be continuous. If you multiply it by 20, it'll still be continuous, just bigger. So let's say b of f of x is also continuous. Let's just call a scalar multiple. Okay, so for example, we know that f of x equals sine of x is continuous. Okay, no matter what value you plug in for x, it'll exist. Then so is, let's say f of x equals 8 times sine of x. Okay, just because you multiply it by a number won't automatically make it discontinuous. Slide that up a little bit. Okay, so for number 2, it's the sum and the difference. Okay, so if f of x and g of x are both continuous, if you add them together, it will still be continuous. If you subtract one from the other, it'll still be continuous. So f of x plus g of x and f of x minus g of x are both continuous. Okay, so for example, let's say if you have f of x equals x. Okay, so we know x is just one long slanted line. It's continuous forever and ever. And let's say we have our g of x equals sine of x. Okay, we know sine of x is continuous. You plug x in for anything and it'll be defined. So that means if we have some h of x equals x minus sine of x, or even if we have some h of x equals x plus sine of x, then they will both be continuous. Okay, so if they were both continuous before, if you add them or subtract them, they'll still be continuous after. Let me slide that up a little bit. Okay, and the third is the product of the two. So f of x times g of x is continuous. Okay, so if you have, for example, let's say f of x equals sine of x, and g of x equals cosine of x. Okay, both of those are continuous. You plug in x for anything, it'll exist. If you multiply them together, it will still be continuous. Oh, why do I keep hitting that? Then sine of x times cosine of x is also continuous. Okay. Now division is a different story. There's possibilities that if you divide two continuous fractions, it will become discontinuous. Okay. So if you had sine of x over cosine of x, if you decided to divide, the two, remember cosine of x can never equal 0. So that means if you have cosine of pi over 2, then it's discontinuous there because you now have sine of pi over 2 over cosine of pi over 2, which is denominator of 0. So that's why you can't do it with division. But it does work with adding, subtracting, and multiplying. All right. Any questions on any of those? Yes.
Can you rewrite a division under word?
Oh, sure. Actually, it would probably be easy to write it down. Okay, so let's say just a quick example as to why the division doesn't work.
Write down a little bit.
Oh, thank you. Okay, so if you have f of x equals sine of x and g of x equals cosine of x. Okay, both of those are continuous everywhere. So if you have some h of x equals sine of x over cosine of x, then you know your denominator can never equal 0. So that means x can equal pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, etc., 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 because those are all the spots where cosine of x will equal 0. Okay? So you can't have any spots where it's undefined for it to be continuous. That was the only reason why. Does that make sense?
Yeah.
All
So
right.
that would just apply to the cosine though, right? Like, technically the sine can still be anything, it's just cosine can't be 0.
Oh, yeah. Yep, but that just, if you did
Right.
get those together, it would create all those little openings. Same way if you had like x and cosine of x.
Right, okay.
All right. All right. Okay, so let's see. All right, so lastly, we'll look at a few strategies for finding limits. Okay, so first could be rationalizing the denominator. Okay, so let's say, for example, if you wanted to find the limit as x approaches 0, square root of, well, actually, this one's the numerator. I don't know why. But you can do the denominator also. Square root of x plus 1 minus 1 over x. Actually, I could have left that there, so it should have been numerator or denominator, but for this particular one, it's the numerator or denominator. Oops. Okay, so remember, when you want to rationalize either the numerator or the denominator, you have to multiply it by its conjugate. And the conjugate is just the same two terms, but you use a different sign. So let's say if you remember the conjugate of, let's say, square root of x plus 1 minus 1 is square root of x plus 1 plus 1. So all you're doing is changing the minus to a plus. If it was plus, you just change it to minus. So that's the conjugate. Okay? So you would just multiply the numerator and denominator by the conjugate. And that's how you would get rid of the square root. So here you couldn't just plug in 0 because it would be undefined. But if you actually just made it like this, the square root of x plus 1 minus 1 over x times square root of x plus 1 over square root of x plus 1 plus 1. Okay, so if you multiply these two just using the FOIL method, okay, so if you have your first, that'd be the limit as x approaches 0. You have basically the square root of x plus 1 squared. The square root and the square would cancel out, so that would just leave you with x plus 1. Exactly. So you have x plus 1. Then your outer, you have plus square root of x plus 1 Your inner is minus square root of x plus 1, so those would cancel each other out. And then your last would be just negative 1 squared, which is negative 1, over x times square root of x plus 1 plus 1. Okay, now if you actually plug in your 0, you'll see the denominator wouldn't become 0 anymore. Okay. So if we plug in our 0, you end up with 0 plus 1 minus 1. Oh, sure. Oh, actually, I missed a spot there. Oh, so forget that step just yet, because I know it's x plus 1 minus 1 is x over x, so those two would cancel out. So skip that step there, and that actually becomes the limit of x over x times square root of x plus 1 plus 1. Sorry about that. So this one and this one cancels out. And that gives us the limit as x approaches 0 of 1 over square root of x plus 1 plus 1. Now we can plug in our 0. Okay, so if we plugged in our 0 here, we would end up with 1 over 0 plus 1. The square root of that would just be 1. So square root of 1 plus 1, which ends up being just 1/2. So bring that up a little bit. All right. So any questions on that one? All right. Now remember, we're not saying that the value is 1/2. We're just saying that as it gets closer to 0, the limit is just 1/2. Okay. Still undefined at 0. It's just we can figure out just where the limit is. Yes.
I'm trying to think this out for a second.
Mm-hmm.
Wouldn't that just be like 0 over 2, or am I just thinking it wrong?
Oh no. With this one, and I can see where that can be mixed up, because remember you have plus 1 minus 1.
Right.
So once you have plus 1 minus 1, that just leaves the x. So you have x over x times the square root of x plus 1.
X.
Yep, and then the x canceled out.
Wait, so if you cancel out the x, then wouldn't it just be? Oh, it would just be 1 of them.
Yep, it would just be 1.
Yep.
All right. Any other questions, or it's kind of sort of making sense? All right. Oh, anyone still writing that? No, okay.
Real quick, sorry. Sorry, real quick, one more question.
Mm-hmm. Okay. Mm-hmm.
You're not multiplying that out for, wouldn't you distribute that -1 to each one, and then that become negative x?
Oh, no, because the only reason is because these two aren't multiplied to each other. Yeah, because remember up here, we did the FOIL method and got rid of the square root, so this is just x plus 1 minus 1. Yeah, so that's why it wouldn't do that. But if it was multiplied, then it would be negative x.
Okay, so then, now here, you take out the parentheses and you just work it out.
Exactly.
Okay.
Yeah. All right. Any other questions on that one, or everybody's
I know
good?
it's very basic, sorry.
All right. Yeah, just those little details can sneak up on you. Let's bring that down. There we go. Okay, so let's say we wanted to find the limit. Say limit of x squared plus x minus 6 over x plus 3.